1 million people living on Mars by 2050. That is not a science fiction novel. That is the stated goal of the most powerful rocket engineer alive today. But here is the question that scientists are asking in laboratories, in NASA research centers, and in the quiet corners of space medicine. Is the human body even capable of surviving Mars? The answer is more terrifying than you think. Elon Musk has a vision, and it is enormous. His company SpaceX is developing the Starship, the most powerful rocket ever built, designed to carry 100 people at a time across 140 million miles of empty space, land them on a frozen, airless desert world, and build a self-sustaining civilization from nothing. He calls it the backup drive for human consciousness, the insurance policy for our species. And when he speaks, the world listens. But science does not listen to charisma. Science listens to data. And the data on Mars, the actual documented, measured reality of that world, tells a story that is far darker than any promotional video has ever shown you. This is not a story about doubting human ambition. This is a story about what ambition must face: the cold, precise, unforgiving laws of biology, physics, and planetary science. This is the reality check. Before we talk about colonies, we need to understand what Mars actually is, not the romanticized version, the real one. Mars has an average surface temperature of -60 degrees Celsius. At the poles, it drops to -125. Its atmosphere is 95% carbon dioxide, and that atmosphere is so thin, the air pressure on the Martian surface is less than 1% of what you feel standing on Earth right now. That means if you stepped outside without a suit, your blood would begin to boil. Not from heat, but from the absence of pressure. Within seconds, you would lose consciousness. Within minutes, you would be dead. Mars has no magnetic field strong enough to deflect solar radiation. It has no liquid water on the surface. It has no breathable air. It has soil loaded with toxic perchlorates, chemicals that, if ingested, can destroy the human thyroid. This is not a fixer-upper planet. This is a world that at every level is actively hostile to human life. And yet, people are planning to live there permanently. Let us understand what that truly means. Problem 1. Radiation. Earth has a magnetic field and a thick atmosphere that together absorb the most lethal forms of space radiation. Mars has neither. On Mars, you're exposed to two primary threats: galactic cosmic rays, high-energy particles from dying stars across the galaxy, and solar particle events, sudden, intense bursts of radiation from the sun. NASA data from the Curiosity rover shows that a 500-day stay on Mars would expose a human to radiation doses exceeding the lifetime career limit set for ISS astronauts, just from being there. And the journey to Mars adds another heavy dose on top. Long-term exposure means dramatically elevated risk of cancer, neurological damage, and cellular mutation. Shielding is possible, but to block cosmic rays effectively, you would need meters of solid rock or water above your habitat. Building that on Mars with no infrastructure in the early years of a colony is an engineering challenge we have never faced before at this scale. Problem 2. Gravity, or the lack of it. Mars has 38% of Earth's gravity. That sounds survivable, but the human body was engineered by 4 billion years of evolution under one specific gravitational constant: Earth's. Studies from the International Space Station show that even in microgravity, which is less extreme than Mars but in the same category, astronauts lose significant bone density and muscle mass within months. The cardiovascular system weakens, vision deteriorates due to fluid pressure shifting toward the brain, the immune system becomes erratic. The critical unknown is this: we do not know what 38% gravity does to a human body over 10, 20, or 30 years. We have never tested it. No data. None. And children born on Mars, their skeletons, their organs, their entire physiology would develop under alien gravitational conditions. No one can predict what that means for their long-term health. Problem 3. Food. Mars receives less than half the sunlight Earth does. Its soil is toxic without intensive treatment. Growing food would require sealed, pressurized, artificially lit greenhouses, consuming enormous amounts of energy to maintain temperature, humidity, and atmospheric composition. NASA researchers estimate that feeding a single person on Mars for a year would require a greenhouse of at least 50 square meters continuously maintained. Scale that to a colony of thousands, and the agricultural infrastructure required becomes almost incomprehensible given the resources available at mission start. And crop failures on Mars are not a tragedy, they're an extinction event for the people living there. Problem 4. The mind. Isolation is not just uncomfortable, it is medically dangerous. Mars is, at its closest, 54 million miles from Earth. At its farthest, over 400 million miles. Communication delays range from 3 to 24 minutes one way. In a crisis, you cannot call for help and expect an answer for up to 48 minutes. You cannot have a real conversation with family. You cannot feel the presence of the wider human world. Psychological studies from Antarctic isolation missions, submarine deployments, and ISS operations consistently show elevated rates of depression, cognitive decline, interpersonal conflict, and judgment impairment in extreme isolation. On Mars, these conditions would be permanent, not a 6-month mission, but a lifetime. Problem 5. Medicine. Every year on Earth, medical emergencies arrive without warning. Appendicitis, heart attacks, broken bones, cancerous tumors. On Mars, there is no hospital, there is no specialist, there is no emergency flight home. A surgical team on Earth cannot be transmitted through a radio signal. The colonists must handle everything themselves, with the training they brought, the equipment they carried, and whatever supplies remain. A medical emergency that would be routine in a city hospital could be a death sentence on Mars, not due to lack of knowledge, but lack of resources. Now, to be precise and fair, Elon Musk is not unaware of these problems. SpaceX's Starship is designed for reusability, which would dramatically lower the cost of sending cargo to Mars. Musk has spoken about building pressurized habitats, establishing propellant production using Martian resources, and creating redundant life support systems. The Sabatier reaction, a chemical process, can theoretically produce methane and water from Martian carbon dioxide and hydrogen. In situ resource utilization, what engineers call ISRU, is a real and promising concept. NASA itself is developing similar technologies. The timeline Musk describes, crewed missions this decade, a city by 2050, is what separates his vision from established scientific consensus. NASA's own roadmap does not project a crewed Mars landing before the late 2030s at the earliest, and that is a single mission, not a colony. The agency's internal assessments repeatedly flag radiation, life support, and human health as the 3 most unresolved challenges. The gap between a crewed landing, planting a flag, taking samples, and returning home is not a gap measured in years. It's a gap measured in decades of solved problems, built infrastructure, and answered biological questions we do not have answers to. Musk's genius is in compressing timelines through sheer industrial force. His rockets are real, his engineering teams are exceptional. But rockets do not solve the human body's incompatibility with Mars. Speed does not dissolve radiation, ambition does not generate oxygen. Even if every engineering challenge is solved, that habitats are built, the food is growing, the air is recycled, there remains the deepest question of all. Can humans remain human on Mars across generations? The first colonists would arrive as Earth-born, physically adapted to this planet, carrying within their cells the biological memory of an oxygen-rich, magnetically shielded 1G world. Their children would be different. Born in lower gravity, under more radiation, in sealed environments, their skeletal structures would adapt differently, their cardiovascular systems would develop differently, their immune exposures would be different. Over generations, 2, 3, 5, the divergence from baseline human biology could become significant, not evolution in any dramatic sense.
Thanks for watching. Subscribe if you like our video and hit the like button.